So without any further delay, our first speaker is Jason Goertzen, Field Experiments on Post-Quantum DNSSEC. Jason?
Hi everyone, so I'm Jason, I'm from SandboxAQ, and I'm going to be talking about some work I did with the folks over at DSEC. Specifically, we wanted to see what would happen, given the new NIST standards coming out for post-quantum cryptography, what would happen if you just made no changes, just deployed it as is, and would it cause any problems? The kind of theory was these things are much larger than classical cryptography, so there's going to be transmission issues, but we wanted to see if this was indeed actual concern. So what we did is we used LibOQS, which is an open source cryptography library that has a bunch of post-quantum cryptography in it, and implemented a bunch of algorithms into bind9 and power DNS. During this talk, I'll mostly focus on bind9, and you'll see why shortly. And then we utilized the RIPE Atlas testing network with about 10,000 probes across the globe, and we queried about 2 million times back in May. What these graphs show are essentially the correct responses, not necessarily like no error R codes, but does the return code make sense? Does the answer section have an answer that makes sense? On the left, we have without the DO bit set, and on the right, we have the DO bit set. And what you more or less see is a classical crypto behaves as you would expect. We filtered for resolvers that could handle classical crypto as kind of a sanity check. But then, as you go into the post-quantum world, Falcon looks quite good, being the smallest signatures and public keys. But then, as soon as you hit dilithium, Sphinx, or XMSS, things start to fall apart. Particularly when the DO bit is set and you're using UDP, it gets really dire for getting correct responses. When we look at non-existent labels, it more or less says the same thing across NSEC and NSEC 3, but as you go to those larger signature schemes, things just get consistently worse. For sake of completeness, we did create a PQC-aware resolver as well that you can go and play with on this website here.
I'm fairly certain they're there.
Okay. I just cherry-picked some results here, but they more or less tell all the same thing. I highly recommend if you want to see exactly what we saw in terms of when the AD bit was set, for example, go to that website. We have a bunch of plots that go into great detail there. Those at IETF, the last IETF, may remember the very scary plots we had, but we didn't want to make your eyes glaze over, so we simplified them for this talk. So the big takeaway so far is that transmission issues appear to be real. It's not just the boogeyman. If you exceed the MTU, bad things happen. In particular, we saw quite a bit of issues when we used UDP and had the DO bit set. And an odd kind of takeaway, we also noticed that 8.5% of our probes claim that the resolvers were able to successfully validate Falcon, which makes no sense because it's not standardized. And I'm pretty sure they didn't magically figure out what our resolver was and switch to it without us telling about it. So that's kind of interesting. So we want to use PQC because quantum computers will eventually exist and we don't want our cryptography to be broken, but we need to keep message sizes relatively small. So what we think, and other folks think as well, is Merkle trees might be a good use case here. Very quickly, what is a Merkle tree? Just as a reminder, a Merkle tree is a binary tree where each node contains hashes. If you're a leaf node, the hash is the hash of some data that you're trying to clump together. And if you're an intermediate node, then it is the hash of your children's hashes combined together. Then if you want to validate if something is part of this tree or is part of this bundle, you'll get this thing called an authentication path, which are essentially the sibling hashes that you need in order to verify. So in this example, if we want to verify that our set 1 is part of this tree, we would hash it. We then take H2, which we were given as part of the authentication path, combine those together to get and hash the combination of those hashes into H5. You then get you're provided H6. You combine those together, hash the combination, and then you get a computed value for H7. And H7 is provided to you as the root node. You then compare what you computed against what the root node was, that you were told the root node was. If they're the same, then you can safely assume that this data was part of this Merkle tree. If they are not the same, then someone's lying to you. So can we apply this to DNS? Well, I think so. And this is how we did it. So we'll utilize the fact that you can have two different types of keys in DNSSEC. Namely, we'll have a KSK, which will just be any other standardized DNSSEC algorithm. In the future, this could be like a PQC like Falcon or something as your KSK. This will provide you with the authenticity integrity you need. And then we'll define a new algorithm, the Merkle tree algorithm, and we will store the root hash of that tree in the ZSK R data. Normally, Merkle trees don't necessarily provide you authenticity, but because the root node will be signed by the KSK, it kind of gets upgraded to have the authenticity property. Then your signatures will become the authenticating path, and this is really nice because they just grow logarithmically to the number of RR sets you have in the zone. So this is a really nice win. And then we also utilize some work from some colleagues of mine from the Batch Signatures Revisited paper that lets us only use half of the hash. And this is a really nice finding that you don't reduce security because of the second pre-image resistance property. So you get half the size with the same amount of security, which is a really nice win. But this isn't just completely a drop-in replacement. We have a couple issues that we need to work on. Namely, there's a circular signing issue. So every time you sign something, your Merkle tree changes and your root node hash changes, aka your ZSK will change. And then every time the root node changes, your key tag will also change, which will affect what you input into your sign and verify functions. So we'll need to be able to handle we'll need to be able to allow our DSK sets to have disjoint algorithms, what we're calling that. And what I mean is that we won't require that the Merkle tree sign the DNS key set, because if you try and sign the DNS key set with the Merkle tree, it changes the Merkle tree, so that makes no sense. So in this case, we will waive that requirement in DNSSEC and just require that the KSK sign the DNS key set, and then any other ZSK algorithms would also sign the set as normal. And then finally, because we can't, we cannot include the key tag into our inputs for sign and verify. So in our case, we for when we're using the Merkle tree, we just zero out the key tag field, since it would change every single time we update the Merkle tree. And we get two nice wins with this. So first, these are the sizes of DNSSEC messages signed by various algorithms. You have the classical crypto on the left with ECDSA and RSA. They're by far the smallest. Falcon is pretty good. And then Dilithium, Sphinx Plus, and the XMSS parameter set we used are not so good. But as you can see, when you apply Merkle tree as a compression technique, they get under the MTU size, the typical MTU size, and then you avoid going over the line of peril. You also get a win or a trade-off for tiny zone transfers. Now, we didn't implement this, but the nice thing is there's nothing private about Merkle trees. So when you do a zone transfer, what you can do is you can transfer everything with essentially a bunch of dummy RR SIGs. Then when your secondary server receives them, it can just build the tree when it receives it, and then verify that the root hash matches whatever you said the ZSK was, and if it does, then they have it. So it really reduces the amount of bandwidth you would need to do a zone transfer, which is quite cool. So what did we see in the Atlas tests? And this is where some funky stuff starts happening. So the astute and detail-oriented people in the room will notice that Falcon and Dilithium are far worse than our May results. We have not been able to identify exactly what happened here because we have not changed the implementation for Falcon or Dilithium at all. The testing environment is exactly the same. It's just when we did reran them this month, they performed 30 to 40% worse, which was particularly interesting. We did look into adding more resources, more cores and RAM, and that did not really affect the results. So if anyone has any ideas about what could have possibly gone wrong here, I would love to hear it. We're going to be digging in deep after this to see if we can figure it out. But that being said, we do see a win for Merkle trees here. If you look at the case where the DO bit was set on the right when using dilithium 2, it's really bad success rate over UDP, or correct response rate over UDP. But when you compress it with a Merkle tree, it matches stock Falcon as well as Falcon compressed with a Merkle tree. So that's quite nice. And when you look at the non-existent label case, it's kind of a similar story. We upgrade dilithium's correct response rate to match that of Falcon, which is quite nice. And finally, I just want to briefly talk about what this required, the changes that this required to the bind code base to allow us to sign. So currently, we only support offline signing. Online signing would be is quite a tricky problem. And we had to make some significant changes to the sign zone utility. So you essentially have to iterate over all of your RR sets, and then build your Merkle tree, and then finalize your key, and then iterate over your RR SIGs again, and then insert the authenticating paths into your RR SIGs and update the key tag fields. The nice thing is, though, it still took half the time to sign a zone using Merkle tree compression with some other signing algorithm than it did to sign the zone with ECDSA, so that's quite nice. And we think there might be other optimization opportunities there as well. So the final takeaways are, in order to use Merkle trees, we'd likely have to change the DNSSEC protocol. It's not just a drop-in replacement, unfortunately. But by defining it as their own algorithm, it means you can hot swap it with anything else. You don't have to, every single time there would be a new algorithm choice, you wouldn't have to then define a new algorithm ID. You could just use whatever that new algorithm is along with the Merkle tree algorithm. So that's quite nice, instead of having to define like a hybrid algorithm ID. Zone updates are quite limited because your zone signing key will update every single time you add something to your zone. So it's limited to whatever your TTL is. Maybe VeriSign's MTL would help with this. And then also DNS key messages, which for PQC can be quite large, are not compressed either. So it's just whenever you're querying anything else. We did see an improvement in delivery, other than up to the point of that weirdness new failure rate. And then also, compared to the stateful schemes, which also tend to use Merkle trees under the hood, you don't have to have a centralized state to deploy Merkle trees. You can just, it's all public info, so you can compute it on whatever server you have. And that's all I have, so thank you very much for listening.
Oh, hello, I see. So I basically wanted to ask, you said that you basically, the signature size grows logarithmically because you include all the path inside the Merkle, this proof, right? Yep. So maybe not a lot of people here exactly follow X of 5.9 developments, but like recently, the Let's Encrypt people have come up with something like they have basically like tiled up their Merkle trees by group, like say groups of 4, and basically they have like started the index base of that. So instead of like getting a full path, you get like an index and just fetch it yourself. I need this tile, and this tile, and reconstruct it yourself. Do you think it would be feasible to do something like this in DNSSEC? So we could fragment very large zones within the protocol itself.
That could be an interesting way to handle it. So yeah, you could definitely, you could apply it, but the pain is then you have another round trip, you have another query to do, right? Yeah. So whether that's worth it or not, will we see zones that are large enough that will cause us to overflow the MTU or not? That's kind of I would have to see that. But yeah, couldn't see why you couldn't do that as like a safety fallback sort of thing for when you do have those large zones that require the large authenticating paths.
Okay. I have one more question if anyone else doesn't. Okay, so another thing is that like after all, we expect caches to like keep some sort of the Merkle tree head, right? But like especially for like public resolvers like Quad9 and etc., they get a lot of queries, and most of them are not like queried again for a very long time. So could that affect the Merkle tree where the Merkle tree head gets discarded but gets queried again? So they can't keep any Merkle tree but have to construct them constantly. Is this something that can be measured, or?
That's a good question. I'm not sure. I'm sure you could measure it, but we haven't. So something to look into for sure.
Okay, thank you.
Thank you.
Elias Heftrich, Athene. Thank you for the talk. I'm afraid my question is slightly off topic because I saw in your measurements that you got like 100% success with the TCP transmissions when it's unsigned or RSA signed. Probably the way you measured it in some way, like I suppose the RIPE Atlas probes are well managed or use well managed upstream resolvers, but the measurements I know, which probably did different than you, are less optimistic about that. Could you explain or maybe give a take on this?
Yeah, so we filtered all of the results that you saw there by probes that answered correctly to RSA. So whether that's over UDP or TCP, so the RSA rate will always be 100% in our results. Because we use it as a sanity check. Because if you didn't answer it properly, then you have no way of answering what we're asking you properly. It was kind of the logic.
Oh, okay, makes sense. Thank you.
So, yep. Thank you.